You know, our sun, it looks so steady up there, right? But it's actually this incredibly dynamic sphere of plasma with a powerful 11-year heartbeat. This cycle is what drives everything from the northern lights to massive solar storms. But what keeps all that immense power in check? Well, let's dive in. So take a look at this. It's called a butterfly diagram, and it's basically a picture of the sun's heartbeat over 11 years. Each one of those little dots is a sunspot. And you can see how they start appearing at these mid-latitudes and then kind of drift down towards the equator over time. It's this super predictable pattern, and it shows us that there's a powerful engine at work deep inside the sun. And that right there brings us to a huge mystery. See, the engine that's creating all this magnetic activity, the solar dynamo, should, in theory, just keep getting stronger and stronger. So if that's true, what's stopping the sun's magnetic field from just growing completely out of control? Why doesn't our star just spin itself into a magnetic frenzy? To really get the problem, you have to meet the engine itself, the solar dynamo. Deep inside the sun, the star's rotation is constantly stretching and twisting magnetic field lines. You combine that with these massive flows of plasma, and bam, you're generating the magnetic field that drives the entire solar cycle. But here's the crucial point. We know this engine doesn't just run away. We've been watching solar cycles for centuries, and yeah, they get stronger and weaker, but they always stay within a pretty stable range. This is the smoking gun. It tells scientists there has to be some kind of natural built-in governor, some kind of braking system that keeps the whole thing from going completely off the rails. And that is exactly what scientists have found. The sun actually has its own self-regulating feedback mechanisms that kick in when things start to get a little too intense. In solar physics, they call this braking process quenching. These are like the cosmic safety features that prevent a total magnetic meltdown. So let's meet the two main players. Okay, so the two main braking systems are called tilt quenching and latitude quenching. The easiest way to think about it is like this. Tilt quenching is like making the levers that power the engine shorter, so they become less effective. And latitude quenching is kind of like moving the fuel source to a spot where the engine just can't use it as efficiently. They both slow things down, but they do it in really different ways. All right, first up, tilt quenching. Sunspots almost always appear in these tilted pairs with opposite magnetic polarity. Now that tilt acts like a lever, helping to generate the sun's main magnetic field. But here's the cool part. During a really strong solar cycle, the average tilt of these pairs actually gets smaller. The levers literally get shorter, which makes them way less effective at building up the field for the next cycle. And the second break is latitude quenching. This one is all about location, location, location. So sunspots do their best work, they're most effective at building the sun's magnetic fields when they're closer to the equator. But during those stronger cycles, they tend to pop up at higher latitudes, further away. It's kind of like moving your best workers way down the assembly line. Their output just gets a lot less efficient. So we've got these two incredible self-regulating brakes that keep our star in perfect balance. And, this naturally leads to the next big question for scientists. Which brake is more important? Does the sun prefer to shorten the levers, or does it prefer to move the fuel? And that is exactly what the research we're diving into today set out to discover. Let's just put the question out there, plain and simple. When the sun's magnetic engine is really revving high, which one of these two quenching mechanisms does it lean on the most to hit the brakes? Is it the change in the sunspot tilt, or is it the shift in where they show up? Answering this is absolutely key to really understanding our star's behavior. And here's the answer. This is kind of like a treasure map. It shows us which brake is dominant under different conditions. That key factor, the thing along the bottom axis, is basically how efficiently the sun's internal conveyor belt is moving magnetic fields around. Just think of it as the engine's overall efficiency. Now look closely and you'll see that crossover point right in the middle. Turns out, when that internal conveyor belt is super efficient, latitude quenching, the red area, is the dominant brake. But if the conveyor belt becomes less efficient, tilt quenching, the blue area, takes over. So the sun uses both, but the balance of power totally shifts based on how well the engine is running. And get this, another key finding boils down to a single number, about 0.36. Now this number represents how strongly these brakes react to the engine revving up. Previous models assumed this value was way up around 2, which would mean a really strong, sensitive reaction. But finding out it's actually much, much lower, just 0.36, shows the relationship is way weaker or shallower than anybody thought. This is a major update to how we fundamentally understand the sun's engine. So we know which brake takes the lead and when, but what happens when they're both working together? This is where the story gets really, really cool. Because together, they don't just slow the engine down, they actually impose a hard limit on its output. This graph right here is the big payoff. That black line shows what would happen with no brakes at all. The magnetic field would just grow forever, totally out of control. But the green line, that shows what really happens when both quenching mechanisms are active. See how the growth just flattens out? It hits a ceiling, a point beyond which the sun's magnetic field just can't grow. And you don't have to take my word for it. As the lead researcher puts it in the paper, this combined action is the sun's natural regulatory mechanism. It's not just a simple brake, it is a fundamental governor built right into the physics of the star that makes runaway growth impossible. The sun is a self-regulating system, through and through. Okay, so this is all really fascinating solar physics, but why does it matter to us here on Earth? Well, understanding these fundamental limits on the sun's activity has some pretty profound implications for our ability to predict its behavior, and by extension, its impact on our varied technological world. So let's just recap the big takeaways here. First, and most important, the sun is a self-regulating system. Second, this ceiling effect created by the two brakes is what keeps solar cycles from spiraling out of control. And finally, really understanding how these brakes work is absolutely crucial if we want to get better at forecasting solar activity and protecting our technology from major solar storms. All of this leaves us with a pretty fascinating final thought. We've just uncovered this hidden governor that keeps our very own star in check. It really makes you wonder, what other incredible, self-regulating secrets is our sun and all those other stars out there across the cosmos still waiting to reveal?